Section 28.5, relativistic momentum. This is something you got to see a little bit in lab when we looked at relativity. And it's that once you start traveling at a reasonable fraction of the speed of light, we start needing to modify our momentum equation. Previously, we calculated momentum with just mass times velocity, and this is good up to a point, but you eventually need to start dividing by the square root factor, square root of 1 minus v squared divided by c squared. And this graph shows that idea, right? We have the relativistic momentum divided by the non-relativistic momentum. And we find that at low speeds, like below 0.1 c, below 10% the speed of light, they agree, it's equal to 1. They have nearly the same value. Very slightly different, but that's minuscule. But as the speed increases and approaches the speed of light, the momentum does not increase linearly. The relativistic momentum is going to increase much more rapidly than the non-relativistic momentum. And so momentum gets bigger than it would without relativity. Without relativity, you'd have too small of a value of your momentum. So let's look at an example of this, the relativistic momentum of a high-speed electron. So the particle accelerator at SLAC, which used to stand for Stanford Linear Accelerator Center, and that's near Stanford University, very close to here, is 3 kilometers long, accelerates electrons to a speed of 0.999999997 c, which is very nearly equal to the speed of light. Find the magnitude of the relativistic momentum of an electron that emerges from the accelerator and compare it with the non-relativistic value. So first, an aside, this accelerator is a real thing. You can drive over it. If you drive up 280 North, you'll be able to, you briefly pass over it and you just see it's this long building that stretches out on either side of the highway. So it's very long and straight. There are a couple other pictures here where there's this beam that's contained inside. It's currently now repurposed for other experiments that are really interesting. Really cool stuff that you can do once you get particles like electrons traveling this fast. This is where I did some research at this facility using the radiation that comes off of particles as they're traveling really, really fast. Like electrons traveling this fast give off really powerful X-rays. So we use that in my research to study our materials, which is pretty nifty. But anyways, let's get back to this example. So if we want to solve this, we have our relativistic momentum equation, so we can plug in the mass of the electron, 9.11 times 10 to the negative 31 kilograms, times the speed. And notice we need all of these decimal places. This is a place where we cannot round, so that can be very tricky. Similarly, in the square root factor, it's square root of 1 minus 0.99999999997 c squared divided by c squared. And it's often easier to cancel the c out first. You still will need to square that 0.999 term, but by canceling the c, then it's not ginormous. So that can help. And what we get is that the momentum of these tiny, tiny electrons is 1 times 10 to the minus 17 kilograms meters per second, which is pretty small, but it's way bigger than the mass of the electron. So this is traveling very, very fast. And we can see, okay, how much bigger is this relativistic momentum than the non-relativistic momentum? Well, the non-relativistic momentum does not have this factor of 1 divided by the square root of 1 minus v squared over c squared. And so when you calculate just that factor, you end up coming out with 4 times 10 to the 4. And that is how much bigger the relativistic is than the non-relativistic. So the non-relativistic is going to be 40,000 times smaller than the relativistic that we just calculated. All right, so we will wrap up that section right there.